Okay, if it starts rubbing against my shirt again, just let me know. I don't hear it up here. So today's straightforward. We do a short lecture, use the rest of the time for group Q&A, and then there's office hours, the usual 12 to 1. So everybody hopefully be super ready for the exam. Any questions on just how the exam is going to work or anything like that? Anybody super nervous? Got your cheat sheets done? 2 sheets front and back, not 4 sheets, single-sided. 2 sheets of paper. Oh, somebody just did 4 sheets. Glue them together. Just glue them together. If you've got them single-sided, then you've got 2 sheets. It'll be close enough. Okay. So we're going to do something called the Qr Factorization. Once you know what it is, you'll start seeing it appearing everywhere. It's based on the Gram-Schmidt process, which we need for the exam. So that's why I'd like to give this lecture today. So Gram-Schmidt, we start with a set of linearly independent vectors. What would we do if the set were linearly dependent? Throw away the ones that we don't need, okay? I mean, if y1 is non-zero, keep it. Then check if y2 is dependent on it. If it is, throw it away. If it's not, keep it, okay? Now, suppose we did Gram-Schmidt and we didn't check linear independence. What would happen? Wow, I should have put that on the exam, okay?
Wouldn't we do like a B that is 0?
Yay! Bravo! Home run. Yeah, I mean, it's not that big a deal. You're going to go down, and all of a sudden, you'll get to here, and you get the 0 vector, and you go, that's not a good one. It's dependent. Throw it away. And then redo V3, okay? So it's not on your exam, but I mean, it's not that tough. So that's why we just assume when we start that the set's linearly independent. And then we use Gram-Schmidt. We produce a set of vectors that are orthogonal. We've not normalized them here. Okay, and then even typically on an exam, I don't ask you to normalize them because it's just extra work. Okay? And I don't really care how well you do calculations numerically. A few, yes, but not a lot of them. Review, I need a matrix A that has linearly independent columns. So that's called the rank of the A of A, the number of linearly independent columns. And of course, that's the same as the dimension of the span of the columns of A. So if this is equal to n, then we have n linearly independent columns, and the rank of A is n. If this was n is 5 and this is only 3, then we have 2 columns that are dependent, okay? No big deal. And then most of you have heard back substitution. Some of us have kind of forgotten. When you're solving linear equations, once upon a time, you may have done something called Gaussian elimination where you made a triangular structure. I don't know. It's not that important. But this is not on your exam, okay? But we need it today. If you have your equations and they're triangular like this, notice how you solve them. You first solve x3. Then you plug that in and you solve x2. And then you plug that in and you solve for x1, okay? That process is called back substitution because you start here and you work your way backwards up the equations, okay? So if I say the term back substitution, that's all I mean is we just take the number, substitute it in, and you're solving scalar uncoupled equations that way because this is one by one, and when I substitute this one in, it's no longer dependent upon this one, et cetera. So it just kind of decouples the equations. Okay, so that's the review material that we need for doing QR. So let's do the QR factorization. Proposition. Let A be, and let me get the size here, M by N matrix with linearly independent columns. So the rank of A is equal to N. Then there exists an M by N matrix Q with orthonormal columns and an upper triangular matrix R and this is N by N. Such that A equals Q times R. That's why it is called a QR factorization, which is kind of, okay, let you write that down. I mean, it's kind of unfortunate when you call something a QR factorization because then you're forced to call your matrix with orthonormal columns Q, and you're forced to call your upper triangular matrix R. So I'll define upper triangular in just a second, but that's what it's called, okay? It's always called that. So upper triangular means the matrix looks like this. Below the diagonal, it's 0. If it's upper triangular and the diagonal elements are not equal to 0, back substitution works, okay? That's the magic of upper triangular. Okay, so just a few notes and then we'll get into this. Notes. One. Q transpose times Q is square. So it's the identity N by N. So just review. Why did we not call Q an orthogonal matrix? Not necessarily square. Yes! Well, you guys are going to do great. Remember, the better the class does, the quicker they are to grade, the happier you are, and the way happier I am. Okay? So I want you guys to get them all right. So yes, if A is square, then Q is square, then this would be an orthogonal matrix. But it still has the property, its columns are orthonormal, so if I take the inner product of any two columns, I get 0. And if I take the inner product of a column with itself, I get 1. Now when I transpose Q, the columns become rows, and so the ij element of this is the ith row and the jth column. In other words, it's the inner product of the ij column of Q. So we'll come back to that, but that's why you get the identity. Okay. Okay, hopefully everybody is familiar with this notation because it is used on the exam, okay? If I have a matrix, the ij element is this. So I throw jth column, okay? So we want this to be 0 when the row is bigger than the column. So that means R looks like R11, R12, dot, 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 R1n, 0, R22, dot, 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 R2n, and then this continues down to Rnn, 0, 0, 0, etc. Okay, so that's an upper triangular matrix. Below the diagonal, it's 0. We love those because of back substitution. And then the columns of A are linearly independent if and only if R is invertible. Okay, that may not be totally obvious at this moment, but as further review, we will get R as the representation of A in a special basis. And then that's where it will all come clear that the columns of R are linearly independent. Yes, question? I said A has linearly independent columns, yes.
So then for node 3, are we already assuming that A is
Yeah, so A linearly independent implies, so now we're going to have that R is invertible.
like always?
Yep. And if you do the calculations without checking that A has linearly independent columns, and you compute your R and it's invertible, then everything was right. That's all I mean, yeah. No, sorry to be confusing. I wasn't aiming to be confusing, but you're right. Yes, we assumed that's our result. You're lazy, you just do the Qr factorization of your matrix and bingo. Yep. Okay. So, utility, what is it good for? Just leave it at that. Okay, so just go back and look. We will do the proof of this because it will practice using Gram-Schmidt. It will practice computing representations of vectors. But while we're fresh in our minds, let's just look at a couple of different applications. So let's look at a set of overdetermined equations. Okay, so we assume the columns of A are linearly independent when we do that. Okay, so let's just write the Qr factorization. We don't know how to compute it yet, but let's just suppose that that proposition is true and see if we get a really nice, clean form for this solution of this overdetermined problem. Okay, so we write this and consider, well, if I am doing unweighted least squares, so just the most basic thing, when the inner product is just x transpose y, I'm going to write this slightly differently, so hopefully you left yourself some room here. Let's do A transpose A x hat equals A transpose B. This will make things a little bit cleaner for us. Okay, so you remember the trick that I taught you before we derived that this was really the Graham matrix, and this is the right-hand side of the normal equations, the beta, and this is the alpha. The trick I taught you was multiply both sides by A transpose, and then the rank of A transpose A, which is now square, would be the same as the rank of A. And we didn't really know how to prove any of that, but now we know all about it. So let's look at A transpose A for a second here. So A transpose A, well, if A is Q times R, the transpose is R transpose times Q transpose. And then we plug in what A is. And then Q transpose times Q is the identity matrix. So we get R transpose times R. Okay, so that's the Graham matrix. It's an upper triangular matrix, and you do the transpose, you get this lower triangular matrix. Let's look at the right-hand side of the normal equations, A transpose B. So that's R transpose Q transpose times B. Okay, so what are the normal equations? They're R transpose R equals R transpose Q transpose B. Yeah, so remember, now we have rank of A equals N if and only if R invertible. So we can cancel one of these, okay? So we just multiply by R transpose inverse, R transpose inverse. Whoops, forgot my X hat, yes. Thank you. And so we end up with R times X hat equals Q transpose times B. And so what? That means we solve for X hat by back substitution.
When R is invertible, we also assume that the transpose of R is invertible.
Well, R is square, so the number of linear independent columns is the same as the number of linearly independent rows. And that's easy to see when the matrix is triangular like this, okay? Because the columns are independent if and only if these diagonal entries are non-zero. Then the rows are independent if and only if too. Okay, so triangular matrices, that's super clear. Then the transpose, you can see how that would work out. Yep. Now, let's suppose we believe that the rank of A and the rank of R are the same. Then this is where it becomes quite easy to check the rank of A transpose times A. I mean, that's the Gram matrix, and we have a theorem that says when the basis we're using, which is the columns of A, are independent, the Gram matrix is invertible, so that gives us the rank of A transpose A, and A are the same there. Okay? Okay, so once you have that, then you can see numerically solving this overdetermined problem. If you do the Qr factorization of A, you multiply by a matrix with orthonormal columns, so that's numerically very nice, and then you do back substitution. Okay, so we call that 1. Let me do something very similar, but a little bit different. Let's suppose A is square and invertible. Okay. We write A equals Q times R. We do its QR factorization. So then A inverse equals R inverse times Q inverse. And, okay, so if A is square, Q then is an orthogonal matrix, and we can put Q transpose here. So this is the MATLAB / command. Okay, so some of you, when you were doing your recursive least squares, you said, I don't like MATLAB giving me these ill-posed things when I'm doing inverses. And so you're very smart about MATLAB, and you just throw in the / command, okay, is what you did. And you said, okay, and because MATLAB will then solve the equations using the QR factorization. And you can see why then, once again, that is nicely behaved, because it takes the columns of A, builds up an orthonormal basis, and then we'll see how to compute these entries in R, but then as long as these guys are non-zero, it has very simple calculations to compute the inverse of A. So that's what MATLAB is doing. Okay, so essentially here, it's the same thing, okay? Overdetermined, and then solving for the inverse of A. They look at almost identical with the / command. Cool? Okay. It'll be more cool when it comes up in seminars you're attending, or it helps you get a well-paying job, okay? I get it, okay? So, let's do one more, the underdetermined, which is not on your exam. Suppose AX equals B is underdetermined. With the rows of A linearly independent. Okay. Our solution to the equation is A transpose A times A transpose inverse times B. This is the X of smallest 2 norm satisfying our linear constraints. Okay, so this is a solution of something that is called a quadratic program, okay? So if you've heard the expression QP, you have solved the simplest possible QP, quadratic program, because we are minimizing the norm, the 2 norm, that's quadratic, of X, such that it satisfies these linear constraints. A general QP has AX less than or equal to B allowed. We'll talk about that at the very end of the class, okay? But this is a special class of a QP, which is cool. Yes, question? No? Okay, so if A has linearly independent rows, then A transpose has linearly independent columns. So that's review. So we write A transpose equals Q times R. Q transpose times Q is the identity. R upper triangular. Instead of A transpose times A, we have A times A transpose. Okay, but it's still equal to R transpose Q times R, because we did the Qr factorization of A transpose instead of A. And then we plug in for X hat. So A transpose QR, A times A transpose, R transpose R inverse. Then we have B. So it's Q, R inverse, R transpose inverse times B. And so the R and the R inverse go away, and we have Q, R transpose inverse times B. So we still have a very simple calculation to do once we've done the QR factorization of A transpose. We get the solution to the QP via Gram-Schmidt, and you'll see very simple calculations with inner products to get the terms in the R. This R is now transposes lower triangular, so fine, compute its inverse, or compute the inverse first of the upper triangular matrix and transpose that. It's the same. Okay, so. Okay, so let's go back to the beginning. Okay, now we're kind of convinced that this thing is semi-useful. Here's my proposition, and I want to prove it. It is not the proof on your exam. That would be way too nice, right? Okay, so, but just think, if I wanted to prove something like this, if somebody gives me a hint that it's true, how might I go about doing it? So Q has the same number of columns as A. So how might I start out with A and produce a matrix with orthonormal columns? Gram-Schmidt with, so I just do Gram-Schmidt and normalization. Okay? Bingo. Now, what's this guy?
Is it just like the eigenvalue matrix of A times
self-equation of the quadrant?
Close. So we're going to see, but what we're going to do is take A, change its basis to being this orthonormal basis, and compute it's that, and then we're going to get this, okay? So it's just going to be the representation of the columns of A in this orthonormal basis. Now, why is R going to be upper triangular if I do that? How does Gram-Schmidt work? I got the first column of A, so I just normalize it to get the first column of Q. Okay? So how is the first column of A related to the first column of Q? They're just by a scale factor, okay? And that'll be the 1, 1 entry of R, because it multiplies the first column here. Now, you remember how Gram-Schmidt worked? I made a really big deal about this. We take the next two vectors, their span is equal to the span of the next two things here, okay? So the second column of A is a linear combination of the first two columns of Q. And so now you have to have two coefficients in there. So now we went to just 1, now we got 1, 2. The third column of A, the first three, is the span of the first three columns here. So the third column of A is a linear combination of the first three columns here. And I get R has that magic structure. So I'm going to write all this down, but I'm just saying I think you guys can see at a high level. You're happy that you don't have to do it in real time on an exam, but you could actually produce that by understanding the properties of Gram-Schmidt. I see some people going like, you know, darn, I can't believe he's convinced me that I can actually do something on my own, okay? I know, okay? All that math is actually paying off. Okay, so how to compute the Qr factorization. We'll do it quick so we have time. Okay, so we just write A equals A1, A2, AN, and the AIs are vectors in RM. So in principle, we have many more rows here than we do columns, just a few columns. The problem is we're looking at things that are like overdetermined equations. The columns are linearly independent. There may be many more rows than there are columns, but there's at least that many rows. And the inner product that we're using on RM is just X transpose Y. So, Gram-Schmidt with normalization, and we don't need normalization in calculations anyway tonight, okay? So it's going to take these vectors, A1, A2, that we always called Y1, Y2, etc., produce V1, V2, Vn. So V1 is the vector A1 over the norm of A1. Let's see if this works for you. V2 is A2 minus, and then I want to remove the projection of A2 onto V1 so it becomes orthogonal. Okay? So that's all I'm really doing. If I take A2, its inner product with V1, and then multiply it times V1, that's the projection of A2 onto the vector V1. Now, why do I not have here divide by inner product V1, V1? Because it's 1, okay? So if we're not normalizing, we just divide this by inner product V1, V1. I could write it here, it wouldn't be wrong, okay? Okay, and then we take V2 and we normalize it. And I'm going to write it just like we would in a program because that's exactly what you would do. You would never give it another variable name, okay? You might, but unlikely, okay? And then VK is equal to AK minus, and then I project AK onto V1. I want to subtract that off of it. AK onto V2, subtract that off of it. Dot, 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 minus AK onto VK minus 1 times VK minus 1. And then I normalize that. Whoops. Okay, so we get these formulas because we're setting VK to be orthogonal. We want to choose it to be orthogonal to V1, V2, V3. So we just remove all the components of this that depend on V1, V2, and so now it's orthogonal. Okay. And then we have span of A1 up to AK equals the span of V1 up to VK. Okay, so that's the special thing about Gram-Schmidt. So this holds true even when we don't do the normalization, and if we don't do the normalizations, we do need to divide by the norm squared of V1 and the norm squared of V2 and the norm squared of VK minus 1, okay? That's Gram-Schmidt. If we don't normalize, and believe me, you don't want to normalize when you don't have to. It's just a bunch of square roots and crazy numbers showing up, okay? So now I take Q and I just stick. So all I've done is taken the columns of A and I've built an orthonormal basis for them, and I use that as the columns of Q. And if I do that, the ij element of Q transpose Q is the inner product of Vi and Vj, and that equals 0 or 1, depending on if I is equal to j or not. So my Q having orthonormal columns, that's Gram-Schmidt. And so the final question is, what about R? Okay, so this is just a review of bases. So the ith column of A is in the span of V1, V2, Vi. These vectors are orthonormal, okay? These guys are orthonormal. So now I want to write AI as the linear combination. So I'm calculating the representation of this vector with respect to this basis for the column span. Normally, when I do representations, I have to write down a bunch of simultaneous equations and solve for the coefficients. But when they're orthonormal, this is just equal to inner product AI V1 times V1, inner product AI V2 times V2, inner product AI VI VI. That's an I, not a J. Those are, I don't know what they are. Dots and some pluses and a colon. I don't know what the colon is doing there for. Okay, so that's what you get when you do the representation, okay? Hence, the representation of AI in the basis V is, I'm calling that RI1, RI2, dot, 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 RII 0, 0. And that's AI V1, AI V2, dot, 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 AI VI 0, 0, 0. Okay, so this upper triangular matrix R, it is just the representation of the columns of A in the basis that we get from Graham-Schmidt applied to the columns of A, making it orthonormal, and then we just read off these coefficients. Okay. And we get Q times, so we'll call this Ri, the representation, the ith column of the representation equals AI, and that means Q times R equals A. So that's it. Right? Q times Ri is just the first column of Q times Ri1, second column of Q times Ri2. That's what we have written up here. And so if I just go A1, A2, AN, I go R1, R2, Rn, and I get QR equals A. Okay, so this is just multiplying matrices times partitioned matrices. So I partition A, I partition R into its columns. So this is the representation of the columns of A in the basis from the choosing an orthonormal basis for the columns of A via Graham-Schmidt, okay? And that's it, that's QR. And that's 45 minutes. So, questions on QR really quick? Did it help you review a little bit of Graham-Schmidt? Questions on representations, maybe? Yeah, question.
So I'm confused with the row versus column orientation of these, because in order to get AI, that linear combination, you would either need to multiply the column vector of inner products with the v's like going across as opposed to going down the column. Is that what Q is?
So Q has V1, V2, Vn times Ri1, Ri2, Rin, wow, would be equal to what? Ri1 times V1 plus Ri2 times V2 plus Rin times Vn. Now for us, Rin equals 0 for Rij equals 0 for j bigger than I. Okay, so it's really it. This is all, this part is homework 1. Multiplying partitioned matrices times vectors, okay? So Q is V1, Vn, V1, It stops at I because the way Graham-Schmidt works, you take the first I vectors to which you're applying Graham-Schmidt, then that's the orthogonal vectors that pop out span that same space. They don't stick out anyplace else. We have this triangular structure when we do Graham-Schmidt. And that's what gives us the zeros down here. Okay? So Q times Ri is this, and that's equal to AI. And so Q times R1, R2, Rn equals A1, A2, An. Cool. So that's homework 1 right there. Other questions on this? Yes, please.
So the result is we think, Q and R for certain vectors.
If A is full rank, this is unique, yes. The question was, are Q and R unique? And the answer is, if A has linearly independent columns, it's unique. Now, you can do the Qr factorization when A has linearly dependent columns, and it's just because we made the observation when we're doing Graham-Schmidt, if we get a 0 here, who cares? Just move on to the 4th column of A, okay, and continue. And then you'll still write A3 as a linear combination of the ones above it, okay? So everything will still work just fine. But when you do your R, you'll get some zeros on the leading term. Okay, R will not be full rank in that case. So we're not doing that in principle, but you guys can easily find on the web all the versions of Qr factorizations for all the different assumptions on A. And they're all the same. And I have a homework assignment later on where you're using the Qr form in MATLAB, so it might not work for some of you people who are not using MATLAB, but you can just play around and see what's going on there. There's an economical version of the QR, there's the full version of the QR, and these apply when A is not full rank. They're different. So that's all. Other questions? Questions on the exam then? How about that? And let me close this. And I've got the exams, okay? So I've got 2016, 2017, I've got solutions, I've got everything you guys want. So are you Q&A'd out? Did you have a good time with Nils yesterday evening? We always party down with Nils. He's young like we are, okay? I get it. Come on, there's this many people in lecture because they're hoping that one or two of you asked a really cool question. So don't disappoint the audience, okay? Somebody, a cool question. Oh.
Can you go to 2017, probably 5, part D?
Sure.
Something about strict norms.
Yeah. So 2017. Mm-hmm. Mm-hmm. All norms are strict. And notice how kind I was. Even the definition was given as a footnote. Because I don't, I didn't want people to miss it just because they didn't copy that one definition on their cheat sheet. Okay, that's all. Okay, so the question about the strict is?
Look. Is it just like you can show a counterexample, like for the maximum or something?
Yeah, because you guys had that homework problem, and then the one norm is not strict, the max norm is not strict, and those are all norms on R2. So it's meant to be a freebie, yeah. What, he gives freebies, yeah? Question?
For 3C, can you go over the proof, the combination of the two spans is equivalent to the spans for the entire space?
So this must be 2016?
No, it's this one. It's x equals, you got it written there.
Okay, yep.
Go over that some more. I have
Oh.
the notes and found it, but one more explanation.
Okay. So S be a subspace. So we proved that for any finite dimensional vector space, the orthogonal complement gives me everything in X. And how we do that is this. So let K equal the dimension of S, okay? If K equals N, then what's the set of all vectors orthogonal to it? It's the zero subspace. Okay, so there's no problem there. So it's still it's certainly a direct sum because the intersection is the zero vector. Okay. So it's kind of trivial in that case. Let's assume K is at least 1, because if K is 0, then it's equally trivial, okay? So, and then strictly less than N. Let V1 to Vk be a basis for S. We can complete that to a basis for X because X is finite dimensional. We complete to a basis for X. So now we have V1, Vk, Vk plus 1 to Vn. Now we apply Gram-Schmidt. And we produce the basis, let's call it V tilde 1, V tilde K, V tilde K plus 1, V tilde N. And then we have the span of, the first K after we do Gram-Schmidt is equal to the span of the basis to which we applied it, and that was S. All of these guys are orthogonal to the first ones, and so this guy's gives us S perp. And so now X equals the span of this plus the span of this. So X equals S plus the span of these guys, which is S perp, and then the intersection, the only vector that's common to S and S perp is the 0 vector, because then the vector inner product with itself is 0. Is this what you're after, kind of, but you're not quite missing?
It was kind of how the problem was written. We just said vectors 1 through 4 are contained within X. To me, it felt like there could be a 5th vector arbitrarily added if we wanted.
Let's see. Well, there could be, but it's always true that X is S direct sum S perp. This didn't use anything about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? And then S intersected with S perp being the empty set, that's not possible. It's got to be the 0 vector. And then since the first 3 of these, S is the span of the first 3, and S perp is the span of this one, so the span of this plus span of this is X. Yeah. So the reason I went through this is just to point out, this is always true no matter what S is.
Okay.
Yeah, no matter what S is, and then you go back and you substitute what they are and you get that answer.
Okay.
Yeah.
So if C is true, then A would be false only when it's a linearly dependent set.
Well, I don't know. Suppose V2 equals V3 equals V1.
Say that again? V1.
We never said these guys are linearly independent,
Okay.
right? Now, V4 is independent of these guys. So V4, okay, unless V4 is the 0 vector, which it could be. So suppose X is the span of V1, V2, V3, then S perp is the 0 vector, okay? But these don't have to be a basis in that case either, okay? So there's nothing in there that's saying anything about the linear independence of those vectors, which is what you need for a basis. You know from this information that the span of V1, V2, V3, V4 is equal to X, okay? That's the only information you have from those vectors. But to be a basis, they don't just have to span X, they need to be linearly independent. And we have no information on linear independence there. I mean, X could be the 0 vector space even, okay? It'd be kind of trivial, but there's nothing wrong with that. But whether I have independence, dependence of those vectors, S intersected with S perp always contains the 0 vector. It can't be the empty set. So that's false. And then X is equal to this span, so its maximum possible dimension is 4, but it could be 0. Still could be 0. V1 is the 0 vector, V2 is the 0 vector, V3 is the 0 vector, then V4 is the 0 vector.
Oh, yeah, that's right. Yeah.
Yeah.
Okay, yeah.
Mm-hmm. Is it working for you now?
Yeah, it's working better.
Better. Okay. Yeah, so the problem only gives you enough information to see this, and then this is always false no matter what. Independent of any properties you're given of S and S perp. 0 is always in it. Other questions? You guys can talk, it's okay, it's cool. This is just Q&A, man. This is not lecture. Please, question.
I want to know about the definition of the semi-positive matrix.
Positive semi-definite matrix?
Yeah, I want to know if there requires a matrix. Does the matrix have to have a zero evaluation? Have to it must have a zero about the semi.
Yeah, so let me. Oops. Okay, the question is about P positive semi-definite. What does it mean? And then how to test for it. Okay, 1. P has to be symmetric. We have not defined, for us, whenever we talk about positive definite or positive semi-definite, we immediately assume the matrix is symmetric. Okay, so this also means it's square. I don't know, so I'm going to assume it's n by n. I got to assume it's something. And so positive semi-definite means for every x and y in Rn, x transpose py is bigger than or equal to 0. So that's the definition. Okay. Now, how to test? P is positive semi-definite if and only if all eigenvalues are non-negative. Remark, P positive definite implies P is positive semi-definite, okay? I think that's partly what you're asking too. Yeah, okay?
So if I know a matrix is positive definite, and the statement says it's positive
Semi-definite, the answer is true.
It's true.
Yeah.
Can you spell out?
Can I spell out? Whoop.
Can we go through on 2016 3C and 4C?
Sure. 2016.
Oh, I guess we already went through that.
That's 17, sorry.
Okay,
No, that's, here's 16. No, yeah. 1, 2, blank page. So 3C?
Yeah.
Okay, I have to remember what the data is. Let XF be finite dimensional, and V1 through V4 is just some set of vectors. We don't know anything about their independence or span or anything. Which of the following statements imply that the dimension of X is greater than or equal to 4? Okay, so C, there exists something in X that's not in the span of the first ones. So, let me get a color. C, counterexample. Suppose V1 equals V2 equals V3 equals V4 is the 0 vector. X is the real numbers, F is the real numbers, I take V5 to be the vector 1, okay? So it's just the usual thing. You're not given any information on the vectors. They can be anything. Yeah, there's something not in there. So it's not 0, because 0's in that span. So V5 is not equal to 0. So if the question was X has dimension at least 1, then it's true, okay? Because V5 cannot be the 0 vector. There's at least one non-zero vector in X. It's got dimension at least 1. Okay. Now D, let's take X equals R2. F equals the reals. V1 equals V2 equals the first unit vector. V3 equals V4 is the second natural basis vector. Then X is the direct sum of the span of E1 and the span of E2. So.
And then 4C.
4C. Okay, so false, we just need a counter example. Okay, so let's do this. Let's take X equals, just for the fun of it, R2, though I think I could do it with R, but I don't care to. S is equal to the unit vector, and M is equal to twice the unit vector. S and M are different sets, okay? So S is not equal to M, but certainly S perp equals M perp, okay? Everything orthogonal because the scalar changes nothing unless it's 0. Yeah. Okay? This orthogonal complement is always a subspace. So it's easy for the subspaces to be equal. They're very big, but these are just can be discrete elements, and so, I just change the discrete elements without changing the span of S and the span of M are the same. Now, if the question said, span of S equals the span of M. So it actually said S perp equals M perp implies span of S equals span of M. Then that's true, okay? So this is true. And it's the usual thing. The key thing is we have finite dimensional. So just take a basis for these guys and you'll find that S perp perp would then be the span of S. So, yeah. Question?
I have kind of a question on the notation on this one. So the way the question is set up is that M is a subspace, if that's correct, or is it a span?
Well, M is, and this one is a subspace, yeah, but S is just a subset.
So when you say S orthogonal, is that just any vector that is orthogonal to the specific vector S? And then
S perp is by definition equal to the set of all X in X such that X is orthogonal to this. That means the set of all X in X such that the inner product of X with Y equals 0 for every Y in S. Okay. And that's what makes S perp a subspace. Because if 2 times x with y is 0, then bring the 2 out, okay? So it's closed under scalar multiplication. And if I have an x1 and an x2 satisfying this, they're sum because I have linearity on the left, okay? So S perp is always a subspace. Yeah. Yeah. Oh, sorry, right in the middle, yeah.
If S perp is always a subspace, then what about the orthogonal complement of the orthogonal complement of S?
So that'll be a subspace.
But isn't that just S?
When S is, it'll be the span of S. So you can show this. We haven't done it in class. X finite dimensional. It's false in general for infinite dimensional. S perp equals the span of S. So you might want, if you want to play around with that, you can do it with the Gram-Schmidt and that argument I did of completing a basis and everything. It just works. Question?
While you're there, can you go ahead and do 4D?
While I'm here, can 4E?
D.
D.
Duck.
Yes, I can. Any other questions on 4C, on the orthogonal complements and stuff? We have 8 minutes here. We're doing well. And the next question is to do 4D. Okay?
I have one quick clarification.
Quick.
The span of S is a subset.
The span of S is a subspace.
It's a subset.
The span is always a subspace. It's the smallest linear, it's the smallest subspace containing S. It's the set of all linear combinations you can build from S. Yep. No, it's just getting all the definitions down. Cool. Okay, so this is 4D. So we have X, finite dimensional, M contained in X, subspace, X and Y, points in X. We let M1 is arg min of M in M of the norm of X minus M. Whoops, that's Y. Okay. And here's the question. Is M1 plus 3 times M2 equal to the arg min of the norm of X plus 3Y? Okay, what is the characterization of something being arg min in an inner product space? X minus M1 is orthogonal to M. Okay? This is if and only if Y minus M2 is orthogonal to M. Okay, so now, question. Let me write it this other way. X plus 3Y minus M1 plus 3M2, is that orthogonal to M? if this vector is orthogonal to M, any scalar times it is still orthogonal. If this is orthogonal to M, any scalar times it is still orthogonal to M. I add them up. Their inner products are 0. The sum has inner product 0. So the answer is this minus this is still orthogonal to M. And that's what the problem is asking you, really. Okay? So it's really just using, and this was one of the exercises that I gave you when we did the projection theorem. This is 4D. Okay, so M1 plus 3M2 is the argmin of x plus 3y, and then the distance is the norm of the error vector, okay? So the distance from x to m equals the norm of x minus m star, where x minus m star is orthogonal to m, okay? Questions on, this is just a projection theorem, okay? And so 4D is just using the characterization of what does it mean to be argmin in an inner product space, and the error is orthogonal. And then the distance is, remember, it's distance is the infimum over all m and m of this, and so, you know, this length of that vector. You're happy, satisfied with that? Okay, I wasn't sure. You're still going,
My mind's off the ball.
you're working on the next problem already. Got it, okay. Me too. That's what happens to me when I make a mistake. I'm not in the moment, okay? I'm not in the moment, so. Others, here's another one.
Yeah, so on the same one, so as soon as you write the norm of x minus m is equal to the distance from x to m, which is what like the problem originally states, we know that that x is the, or that m is the argument. Like we can rewrite the what's stated in the problem as the argument implementation.
Let me see if I get the basis of the question. Yes. Yes, that's part of the projection theorem. If this achieves the minimum distance, that's if and only if x minus m1 is orthogonal to m. Yes. So let me add that to the solution. Norm x minus m1 equals distance x to m, and that's by definition equal to the infimum over little m in m of the norm of x minus m, if and only if x minus m is orthogonal to m. So it's the same thing as argmin. Yep, that's the projection theorem. So all of those things are contained in the projection theorem. We first proved the pre-projection theorem that said, if this is true, then this has to be true, but we didn't have the other way. But the finite dimensionality and the completing of basis allowed us to assert that there's always a solution here. So we first characterized it and understood orthogonality is like super important and stuff. Okay, so I think we're out of time. We got 4 seconds, so I'll be doing office hours now for the next hour. If you have other questions, put them on Piazza. Nils and I will do our very best to follow them all the way up until the exam. During the exam, we are not answering Piazza. Let me promise you that. Thank you.